Okay, to do part AII, to determine the magnitude of the force applied, of the applied force required to move the loop at a constant speed, I need to think about first what direction the current is acting in, and then two, what's going on with the forces. So right now, this loop of wire is moving at a velocity v into this magnetic field. Well, as it does that, we talked about in the last video that nature does not want that change in flux to take place. Right now, I have more and more area with magnetic field going into the board. So to try and fight that, I want to create a magnetic field that runs out of the board. The way I'm going to do that is if a current is induced that runs this way, runs counterclockwise. Because if I apply the right-hand rule to that, point my thumb in the direction of the current, my magnetic field would be, my induced magnetic field, B induced, would be directed out of the board within this region. And that's what I want, because that's going to try to keep my flux constant. Okay, so then I have to start looking, well, if I have a current flowing this way. Last week we talked about the idea that the force applied by a magnetic field on a current carrying wire is IL cross B. Right now I am taking a current carrying wire and I am moving it in a magnetic field. And that current and that magnetic field are at right angles to each other. I'm not worried about the magnetic field that's being induced by this current in the wire because that field doesn't exert a force on the wire that's creating it. I'm only worried about the force exerted by this external field on that current carrying wire, okay, and on the current in that wire. So the first thing I do is look at this cross product to make sure I and B are perpendicular. They are. The second thing I do is I look at each segment of the wire loop and make sure I know what direction the force is acting on each segment. So right hand ruling it, point my thumb in the direction of the current on this segment, point my fingers in the direction of the external magnetic field. The force on this lower segment of wire would be up. Doing the same right hand rule, point my thumb in the direction of the current, point my fingers into the board in the direction of the external magnetic field. The force on this top segment of the wire would be down. Guess what? Those two are going to cancel and there is no net magnetic force up and down. Now on this external chunk, or not external, but on this vertical chunk of wire, I have a current up, I have magnetic field into the board. There, I do have a magnetic field and it's directed to the left. Okay? That seems to be an unbalanced force. That's the force I care about. So I only care about the distance from here to here when I'm looking at the length, because that's the only length that has an unbalanced force applied to it. So the magnitude of my magnetic force is going to be the current in that wire, which I just figured out. It is B times H times V over R. And looking at my list of things I'm allowed to use, I'm allowed to solve in terms of B, W, H, V, and R. So far that term is good. The length that I care about is the height H. And the magnetic field that I'm being placed in is B. So all of those things work. It looks like I have an answer of the magnetic force is B squared H squared V over R. And what direction is that force? Well, the force being applied by the magnetic field is B squared H squared V over R to the left. So the force required to make it move at a constant speed is that much directed to the right. And this is force applied. So the force I need to apply to move loop at constant speed. Hopefully that blue shows up okay on your computer screen. Let's keep our fingers crossed. Okay, part B. On the axes below, plot the following as functions of position x of this stuff. So on these axes below, I need to take a look at all that. All right, well, I'm going to have to scroll down a little bit. So let's see if I can get a better picture of this. Yeah, we're going to have to think about that. Okay, I want to plot the induced current yeah, in the loop as a function of position x. So I'm going to be scrolling up and down as I explain this, of the right edge of the loop. So for the right edge moving from 0 to W, nothing's going to happen because this hasn't moved into that magnetic field yet. So if I'm looking at the induced current in the loop, initially, as that right edge goes from 0 to W, nothing's going to happen. Okay. As I go, let's see, as I go from W to 2W, that current is going to be, I think we found in the earlier part of the problem, I think that current was going in a counterclockwise direction. We can jump back a couple screens and take a look at that. Yep, it was going in a counterclockwise direction. Okay, they want us, as we plot these, let counterclockwise current be positive and clockwise current be negative. Forces to the right positive, forces to the left negative. So initially our current was counterclockwise, that's going to be a positive current. So if we jump back a couple screens, when we go to plot that current, our current is going to be jumping up to a positive value the whole time that wire, that left edge, the whole time the right edge of that wire is moving into there. So the whole time this front edge is making its way into this material until this whole thing is now between W and 2W. I'm going to have a change in flux, so I'm going to have that current, and I would have this force. Okay. Once it's in here, so once this back edge gets to W, as the front edge moves from 2W to 3W, I'm not going to get anything because now my flux isn't changing. So there's no current, nature is happy, life is good. So from 2W to 3W, I go right along and get back to 0. Okay. But as that front edge starts to leave, now I've got another situation. In fact, I'll leave it there for now. As that front edge starts to leave, now I have a decreasing magnetic flux. Well, nature, which didn't like my increasing flux before, now doesn't want it to decrease. It got kind of used to what was going on. So now I want to create a magnetic field that's going to be stronger than just this external field because my area that's enclosed, which is this, is decreasing. To do that, I'm going to get a current flowing in the opposite direction. Okay, and that's because as I point my thumb along this right-hand rule in the direction of the current, my fingers then, showing the direction of the induced magnetic field, would be into the board. This is my B induced again. And that is just going to strengthen, that magnetic field in that region. So even though the area is decreasing, the magnetic field is increasing, trying to keep the flux constant. So that's going to be, this will be the direction of my current. So if I'm looking at, again, plotting my current, it's now flowing clockwise. My current should jump down here. Okay. And then as a final step, once that front edge gets to 4W, the back edge is at 3W. Now that thing's moving out in a region where there's no magnetic field again. So now I should jump back to 0. Okay. My force is going to be similar. Things that they said, let counterclockwise current be positive, clockwise current be negative. Okay. Forces to the right should be positive, and forces to the left should be negative. And they want us to do the force required to keep the loop moving at a constant speed. So we're going to have to be pulling this to the right. So initially, again, same thing. I didn't have a current, so there's no force on that thing. Then it's going to jump up to that value that we calculated in part A, II. And then once we're in there, we have no current being produced by our previous section. No current being produced here, so no force on those wires. Then the only thing to go back and check is see what direction that current is what direction the current's flowing, and thus what direction the force is flowing on the piece of wire here. Okay, right in this situation, I have current flowing upwards in a magnetic field directed into the board. So the magnetic field is exerting a force on this part of the wire that's still in the field that's directed that way. That's my force magnetic still. Okay, thumb up, external field into the board, force would be that way. So I'd still have to be applying a force to the right. So my force should jump back up and still be directed to the right. It should still be positive. And then after 4W, that front edge is out of there, and so my graph looks like this. So that would be the end of that problem. It's only 2 parts, but it definitely is a challenge.